Hello and good afternoon. On behalf of GmbH Power Electronics, I would like you to welcome to another episode of our experts webinar series. Today's webinar will be held again together with our partner company Proton-Electrotex from Oral, Russia. The topic is powerful low-inductance IGBT modules for transportation and industrial applications. In the contrary to our announcement, 𝗍𝗵𝗽𝗁𝗍𝗍 will be not our guest today. Instead, we will welcome Mr. Kirill Volobuev. Kirill is the head of the IGBT development department at Proton-Electrotex. My name is Ralf Jessler, and I'm in charge of the business development at GmbH Power Electronics in Mannheim, Germany. In the following, I'd like to take the opportunity to briefly introduce the company GmbH Power Electronics. This short presentation summarizes our main competencies and our offer. I think most of today's participants know us as a distributor of power electronic components. Beyond the sales activities, however, our highly qualified sales team offers a comprehensive support throughout the entire product lifecycle. In addition to the product portfolio of our trading partners, we also have in-house products such as complete converter stacks or power supplies with reinforced insulation technology. Furthermore, at GmbH, we develop and manufacture assemblies and systems according to customer specifications, usually in range of approximately 100 kilowatts to megawatts per converter stage. Let's have a look at our components program. Our offer includes gate drivers from Power Integrations Switzerland, power semiconductors from Proton-Electrotex, Russia, from Fuji Electric, Japan, and from Hitachi Energy, Switzerland. Furthermore, we offer high-performance air and liquid heat sinks from MiXM, Italy. Then we offer DC link and energy capacitors from Electronicon, Germany, and from the Chinese manufacturer Shanghai, power resistors and high voltage resistors from 𝗵𝗵𝗽𝗁𝗍𝗂, Austria, as well as current and voltage sensors from MiXM, France. If you use IGBTs or silicon carbide MOSFET modules, such as those presented today by Proton-Electrotex, the thermal foils from our partner NeoGraph from the United States could be a good alternative solution. The compressible graphite foils possess the thermal conductivity that matches traditional thermal pastes. Assembly and disassembly of the modules are reproducible and generally a clean thing. As already mentioned, at GmbH Power Electronics, we sell our own solutions such as plug-and-play driver cards for thyristors and IGBTs, which we also like to use in customer-specific developments. Then our modular converter system VARIS, available in different converter topologies and cooling modes. And finally, our inductive power supplies, which enable the isolated power supply of electronic assemblies at different electrical potentials. The power supplies are partial discharge free up to 21 kilovolts. What differs us clearly from our competition are the activities in the field of development of power electronic assemblies and complete systems, optionally with or without control. Today I'm presenting a fully controlled thyristor bridge for high power motor drives. The bridge is designed for the operation at 600 volts AC and is capable to carry currents up to 4,200 amps DC. The thyristor discs, by the way, are coming from Proton-Electrotex. If requested, we are also happy to manufacture power electronic assemblies or systems at our location in Mannheim, Germany. We are very flexible with regard to the number of pieces. This slide gives an overview of our selected customers. We would be very happy if we can place your logo here soon, if not already done. Okay, thank you very much for your patience. Let's start now with Kirill presentations on powerful low-inductance IGBT modules for the transportation and industrial applications. Hi Kirill, are you there?
Yeah, hello Ralf, hello everyone.
Hello, Kirill. Then please start with your presentation.
Yeah, thank you, Ralf. Last week we spoke about some new products in like mid-power range from our company. Now we are going to present a family of module MiXM. Instead of last presentation, this module is rather more deeply in R&D right now, and we are going to develop it maybe whole next year, but somewhere in the middle of the year we will be ready to start produce some samples to send them our clients or clients of GmbH for internal tests. Let's go on. So what is MiXM module? It is a well-known footprint and case design in the market right now, and our competitors are also develop such modules or even start production of it. And we also see a lot of opportunities in such design, and just a few words from where such design appeared. You know that like common modules types like 34 millimeters wides and 62 millimeters wides modules are rather not up to date, has not up to date design. They were developed maybe 10 or 15 years ago, or maybe more, and they are not so good with modern chips as they could be. And unfortunately, its design of terminals mainly can't is not so good for new chips, which are very fast, and the inductance of such modules are rather high. That's why everyone were thinking about redesigning such modules to achieve the new tasks from a market. And these tasks are to build more powerful and more faster module. And such type was invented. It's what we called in our company MiXM, or like other companies call them, for example, in Finland it's 𝗏𝗵𝗽𝗀𝗃, or maybe like Asian companies like Mitsubishi Electric called it LV100 modules. So the design of it, the design of case and the design of its footprint is open, and everyone could start producing such a module with such dimensions. But of course, what is built internal is our own design, and I guess each company has its own solution in it. So why we choose, as you know, there are two types on the market of such case design. They differ mainly connection of auxiliary terminals of the terminals to the driver board. What we choose is like Infineon, let's call Infineon type, because they're maybe first who invented it. And in contrary, like ABB has another type of design of terminals to the driver board. But we see that our market, our Russian market, especially, is going to like Infineon design, and we suggest that it will be better to start from this design, and we hope that we were right, because to redesign these channels will be rather challenge for us. And it's not just to change a cover of a module, yeah, but also practically all internal parts. Okay, it's just a few words about how it appears and what is inside. Inside is usually half-bridge type module. For sure, as I said, it built in low inductance design, especially for DC terminals, of course. It's designed easy to parallel with maybe 2, 3, or 4 modules in one inverter. We will speak about it further. And our own thought was that we need 2 types of this module. First is for traction. For sure, is mainly on the market. It's with okay, let's call it with AlSiC baseplate, and another one is with copper baseplate. It's for industrial application where not so heavy cycles and not so fast cycles are. And the power of module is more essential than its cyclability. Here you can see just its dimension. We prepared several data sheets, preliminary, of course, data sheets. We will further investigate this module to do more tests this and next year, and of course there will be more information in such data sheets, but nevertheless they are ready and we can send you if you want this data just for reference. Okay, as I said, it's a half-bridge circuit. What else it has? It has 2 terminals to an NTC thermistor inside module. And for example, if to compare such module with Econodual type, or how we called it, MIDA type, which also has NTC inside. In this Econodual type, NTC is placed in the corner of a module. Unfortunately, it's the only place in a module where it could exist because of just board design, and no one in the market could place it in another place in such type of module. In this module, it was suggested from its appearance that NTC will be built in the center of the module, and the same did we. So this NTC thermistor are placed in the middle of the module where the main heat appears, yeah, and the measurement which is done by NTC are more accurate than Econodual type. It's also one of the benefits of this design. For sure, it has auxiliary terminals for gate emitter and also collector of each bridge for the module to check all waveforms of voltage, over voltage, and so on, in order to driver board could more accurate turn off module, and it will not lead to some disasters like damage of module or damage of inverter. Okay. As I said, one of the main benefits of this module that it has low inductance DC terminals. You can see here how it is built in our module. In other modules of other companies, I guess it will be a little bit different, but in common what we have is low inductance, as these terminals are placed in parallel, and I guess it's the best solution which is now existing on the market. I speak about like middle power and high power modules. Of course, in small modules there will be another designs, but this module has about 10 nanohenry inductance DC between DC terminals. Which leads to the thought that such module could be used as with silicon IGBTs, fast silicon IGBTs, for example, last generation of them, as well as for hybrid modules where anti-parallel diode is Schottky silicon carbide diode, and even for full thick modules where instead of IGBTs are used silicon carbide MOSFETs, and which are maybe 10 times faster now than common silicon IGBTs. And with such design of terminals, we wouldn't have such oscillations as first silicon carbide modules has, for example, in common 62 millimeters wide module design. And we also has thought to develop silicon carbide modules in such design, but it will be next step. Our first step will be to produce silicon IGBT module, and maybe in the middle of next year we are thinking of starting to develop silicon carbide module. Of course, it won't be fast, but as we have a case which suits silicon carbide, I guess it will be faster than to develop such a module from the first step. Okay. As I said, also, this module is built for easy paralleling in inverter, just to multiply its power. It has AC terminals in Y side, and then two DC minus and DC plus terminals in other side of the module. So it's easier to place a DC board in this side of the module, and for sure AC board for another side. And DC board or DC board or DC terminals also could be done with very small inductance to receive as minimum overvoltage as possible. And in the middle of the module, there could be like one driver board or 3 parallel driver boards, which could be connected to each other, and all modules will drive from one signal, and it also makes it more faster and more reliable. Let's go on. About our module lineup. As I said, we are thinking about two types of module, for traction and for industrial application. So 1200 voltage, we have 1200 AlSiC for traction module, and more powerful 1400 amperes module with copper design for industrial application. As well, the same, practically the same with 1700 volts. There are 1000 and 1200 amperes modules. Of course, we are working to even to design even more powerful modules in such case, but I can't say that we are ready to make some data sheets for it. Just ideas right now, but maybe in some months or half a year, we could speak about more powerful modules in such design. And as well as we are thinking about high voltage modules in such design. I'm speaking about 3300 volts modules, which we are also working now, but the same as I said, we are not ready to present them because there are lots of internal tests, and well, today's data is not so reliable to just present to you. It's the only thing why we didn't put such type modules in this presentation right now. So let's speak about it maybe somewhere closer to PCIM 2022. Okay, so earlier I said for two types. For sure, it's the first benefit of AlSiC baseplate is thermal cycling capability. AlSiC has better thermal coefficient, but in contrast, AlSiC has higher thermal resistance, which makes these modules little bit, let's say, little bit less powerful than we can build with copper. Okay. What technologies we use in such module? As I said a lot about cyclability. For sure, we were using ultrasonic welding of power terminals to make direct copper to copper diffusion. I know that some companies, maybe because it's just their also research, their first modules in such design are with soldered joints, but I guess it's not a right decision if we speak about traction design modules. Yeah, and at the same time, this joint not only reliable, but also has higher mechanical strength. So it's much harder to damage this joint by any vibrations, which are very high in, for example, train or metro. Okay, next, as I said also about base plates. What we made right now is base plates and DBCs with 6000 volts insulation. But we are also working to make it more higher and make about 8000 volts insulation. But it's also undeveloped right now. To compare these modules with another designs, you can see the table where on the left column is MiXM modules with AlSiC copper base plates. And the second column, there are pin-to-fin replacement. As I said, we suggested Infineon type of case, like 𝗏𝗃𝗃2 or LV100. For example, other competitors has a design which is closer to ABB design. And indirect replacement, it's more interesting. For sure, MiXM module is further generation of, like it's called on the market, IHM modules, like it's called in Infineon. But it also has some benefits and can be used instead of, for example, Econodual type modules or prime pack modules. And in comparison with prime pack, I guess it's a new design, has all positions which are better instead of prime pack modules, because prime pack, how it was designed, just a long 62 millimeters module, which one common bus bar, but it has rather high inductance. We are not only developing module itself, but we also designing drive board. You can see a picture of some one of the first samples of module and with board. And here you can also see main features of driver, our driver, which now is built to 1700 volts module, but in further generation, or let's say this is the second type of this board, will be suitable for 3300 volts modules, which we are also designing. Okay, and if you have any questions about drive boards, or would like to maybe to have another presentation about drivers, just type in chat or on an email, and we can make another presentation about our whole range of drivers, for example. Okay. And about project timeline. As I said, today we're ready with preliminary data sheets, and we also calculate price indication of modules. Right now we make different tests, like reliability tests, for example, and also a safe operation area tests to check everything. And I guess it will last for at least half a year, or maybe a little bit longer. And as I said, here is written that samples will be available in the end of next year. But my thought is, let's speak about it a little bit earlier, because we need to, as we are only on research and design stage right now, we need to prepare our production line to. Okay, this was all from my side.
Okay, thank you very much, Kirill, for this very interesting presentation on your MiXM IGBT modules. We have a first question from Roman. Roman is asking, are you going to develop 600 volts modules as well?
I need to say that there aren't in our roadmap for next year. There is no modules 600 volts. But if you speak about general case design of module, we can discuss it. And even if we haven't such design of case, we can discuss it, but we need to understand that the demand of such modules should be rather high because to start developing it, because each developing it is tests, and tests are usually made for a year.
Technical question. You showed us your line card with modules with 1200 volts and 1700 volts, and you briefly mentioned 3300 volts. Maybe can you let's say give an overview which voltage classes you will add to the line cards in future? What is the planning?
Well, as I said, in this case design, we are going to develop 1200 volts, 700 volts. It's already done, and we are in test conditions. We are designing 3.3 kV modules. We are in our roadmap for next year. There are modules in different case design, in different just a moment, different case design, but with the same footprint. There are such modules on the market, and maybe Infineon has right now such case design. As far as I remember, it's 𝗵𝗵𝗽𝗀𝗃 module, if I'm not wrong. Yeah, and these modules will be for 3.3, 4.5, and 6.5 kV chips. So it will be a higher voltage than now. About 600 volts modules. In such case, we are not thinking right now, because we see no such questions from our clients, or
so no market for big market for this.
Yes, but everything changes fast. So if you have such position, to build such a module, why not? Let's discuss.
Okay. Another question: why have you chosen to develop the XIP type module instead of what ABB calls, or Hitachi Energy nowadays calls, lean pack?
Yeah, we saw two types of modules which were developed, I guess, parallel. In our company, we call it Infineon type and ABB type, or as you said, Hitachi type, right now has. We even start designing ABB type module, but we see that this design has more strong position on the market, and we need to choose one, of course, because, as I said, it's not only a cover which changes in it, but all internal connections. That's why we need to choose one, because we're not ready to produce, let's say, one module with two different driver boards. Yeah, so it's mainly was task from the market to make such connections to driver board instead of ABB type.
Okay, thank you very much. So at the moment, I see no further questions. So then let's close the Q&A session. Anyway, if you have more questions or comments, please don't hesitate to contact me or one of my colleagues from sales. Okay, so there's no question. Then thank you very much for your participation. Thank you, Kirill, for your presentation. Take care, goodbye, and hopefully welcome. See you again. Thank you.
Thank you.
Bye-bye.
Thank you, everyone. Goodbye.